So this is a lovely little question involving connector particles and friction. And what we've got is we've got a ring around a rough vertical pole, and it's connected by a rope which goes over this smooth horizontal pole and is attached to a weight. And at the start of the question, we're told that this distance here is 1.2 metres, and if the ring is 0.5 metres below the peg, okay, it hangs in equilibrium with no friction. Okay, and we need to work out what the weight of this mass here is. So, if it's in equilibrium with no friction, these are the only forces that apply, and we're going to resolve this ring vertically. But first we need to find this angle. So, forgetting about forces, we're going to use the fact that this is a right angle triangle and say that tan of theta is opposite over adjacent and work out our angle to 67.4 degrees. We can use this then to resolve the ring vertically, which will be T cos theta is equal to 50 newtons. Rearranging all of this, it gives us our tension of 130 newtons. And if we come back to the original diagram and look just at this weight here, you can see that's in equilibrium, so T is equal to the weight, so W is equal to 130 newtons. The next part of the question says that if the ring is on a parallel, is exactly perpendicular here, okay, the system is in limiting equilibrium, which tells us there is friction. So looking at the ring, the weight would naturally want to drag it down, so the friction must go up. Resolving this ring horizontally, we can see that the tension is exactly equal to this reaction force, tension to the reaction. We know, as before, that the tension is equal to the weight, which is 130 newtons, so my reaction force has to be 130 newtons. Limiting equilibrium is F limiting is the same as F max, so friction's its maximum, which means it's equal to mu r. Resolving the ring now vertically, friction maximum is equal to the weight pulling the ring down. So the friction is equal to 50 newtons. Remembering friction's mu r, so mu r is equal to 50, we know r is 130, so rearranging this gives me a mu of 5/13. Then the last part of the question goes on to say that if the ring is now brought down, so it's 0.9 metres below the peg, will it stay in equilibrium? Right, we've got to think about what's going to happen here. We've got a tension keeping it up, weight pulling it down, and we know that it was in limited equilibrium earlier. If it's going to move, this tension is going to pull it up, so we're going to think that the friction is going to come down here. Okay, we need to find the new angle, exactly the same as before, using this right angle triangle, gives me this angle to be 53.1 degrees. Now, same as before, the tension is equal to the weight, so that stays the same at 130 newtons. So I'm going to resolve the ring again vertically. T cos theta is equal to weight plus friction. T cos theta is weight plus friction. I know T, I know theta, so I can arrange this to get that in this scenario here, the friction is 28 newtons. Now, is that less than or equal to the maximum friction can be? Let's have a look. Maximum friction can be F max is mu r. Mu we know to be 5/13. Now, the reaction is going to be that way. Okay, remembering that it's always perpendicular to the surface, so that's my reaction. So my reaction is going to be equal to T sine theta, resolved in that direction. So 5/13 times T sine theta, or cos 90 minus theta, the maximum friction can be in this scenario is 40 newtons. That's greater than we said it would be, therefore yes, it can stay in equilibrium.